Hello guys, today I will be explaining the question minimum swaps to make sequences increasing to you. We have been given two arrays A and B. The end goal of the question is to make both the arrays strictly increasing. In order to do so, we can do swaps. For any index I, A of I and B of I can be swapped. The question asks us to return the minimum number of swaps required to make both the arrays strictly increasing. I think the question is sufficiently clear now. Let us look at the approach. Just a moment. Okay, so as we know, we have two inputs, that is A and B, two input arrays. Let's define another array called swaps. So swaps of I basically represents the cost to make both the arrays strictly increasing until the ith index, and there will be a swap at the ith index, that is A of I comma B of I will be swapped, and it represents the cost to make both the arrays increasing until the ith index, until I, basically I included. Okay, and there will be a swap at the ith index, that is A of I and B of I will be swapped. Let's define another array called no swaps. Okay, so no swaps of I basically is the cost to make both the arrays strictly increasing until the ith index, and there will be no swap at the ith index. That is, there will be no swap between A of I and B of I, and it represents the cost. It represents the cost to make both the arrays increasing until the index, until I. So this is the prerequisites to understand the approach I will be explaining ahead. So let me just lay some more emphasis on it. Swaps is an array. Swaps of I represents the cost to make the array increasing until the index I, and there will be a swap at the ith index, that is A of I and B of I will be swapped. No swaps is another array. No swaps of I represents the cost to make the array strictly increasing until the ith index, such that there is no swap at the ith index, that is A of I and B of I will not be swapped. So I think the prerequisites are pretty much clear. Now let's look at the actual approach which uses these prerequisites. So as we already know that we have two input arrays A and B. These are the indexes. Let's lay emphasis on the I minus 1th index and the ith index only. Okay, so I will make things sufficiently clear by discussing each and every case in a lot of detail. So let me represent the first case now. So the first case, I will be writing it over here. The first case is A of I is greater than A of I minus 1, and B of I is greater than B of I minus 1. So basically, essentially what I am saying is the element here is greater than the element here, the element here is greater than the element here. Now, if you see, both the arrays are strictly increasing until the index I already. So one option is to not do any swap here and to not do any swaps here. So what does no swap of I mean? It means that until here we are going to make the array increasing and there will be no swap here. See, if there is no swap here, with this case in the combo, there should be no swap here also. So basically our problem to find out no swap of I, it boils down to finding the cost to make both the arrays increasing until here, such that there is no swap here, which is nothing but no swap of I minus 1. So it's equal to no swap of I minus 1. Let me just repeat this point. We want to find no swap of I. No swap of I is basically the cost to make both the arrays strictly increasing until the ith index, such that there is no swap here. Now, according to this condition, if there is no swap here, there should be no swap here also. So the problem boils down to making a strictly increasing arrays, both of them, until the I minus 1th index, such that there is no swap here, which is nothing but no swap of I minus 1. So this is our first equation that we have got. Now let us look at the second sub case under this case itself. Now, so let me explain you. So what is swaps of I minus 1? Right? This is an interesting case. So I'll use a different color over here to explain so you don't get confused. Swaps of I minus 1 is basically the cost to make the array increasing until here, such that there is a swap here. Okay. Now let us say, what is swaps of I? Swaps of I is the cost to make the array, both the arrays increasing until here, and there will be a swap here. Now see, according to this case, if there is a swap here, then there has to be a swap here also. Now lay emphasis very carefully with this condition. If I want to find swaps of I, that is the cost to make the array increasing until here, such that there is a swap here, it is the same thing as finding the cost to make the array increasing until here with a swap here plus 1, because of this one extra step. So I can simply say swap of I is swaps of I minus 1 plus 1. So this is our second equation under the first subcase. So let me just re-explain quickly both the cases so that it becomes sufficiently clear for you. So no swaps of, first we have to find no swaps of I, which means until the ith index both the arrays must be strictly increasing and there must not be any swap at the ith index. Now if there is no swap at the ith index, according to this condition there should be no swap at the I minus 1th index also. So our problem boils down to no swap of I minus 1, which is to find the minimum, not the minimum, the cost to make the arrays increasing until the I minus 1th index, such that there is no swap at the index I minus 1. So the first equation is justified. Let's justify the second equation that I've written. I want to find swaps of I. What is swaps of I? Swaps of I is the cost to make both the arrays increasing until the ith index, such that there is a swap here at the ith index. If there is a swap at the ith index, it also means that there has to be a swap at the I minus 1th index. But wait, if I swap simply at the I minus 1th index, the arrays behind might not be strictly increasing. So wait. So what I will do is, I will find swaps of I minus 1. What swaps of I minus 1 basically means is that it's the cost to make the arrays increasing until the I minus 1th index with a swap here. Now for swaps of I, in addition to this, I am just making one extra swap here with this condition. So swaps of I will simply be swaps of I minus 1 plus 1. Let me explain you this a bit more clearly, as I think I fumbled a little. So we want to find swaps of I. So before finding swaps of I, let me explain what swaps of I minus 1 is. Swaps of I minus 1 is a cost to make both the arrays increasing until the I minus 1th index, that is until here, such that there is a swap here. Now with this condition in picture, if there is a swap here, there also must be a swap here. So, and if there is a swap here and the arrays are becoming strictly increasing until here, isn't that swaps of I? So can't I simply say swaps of I is swaps of I minus 1 plus 1. Let me go over it again. So swaps of I minus 1 is the cost to make the arrays increasing until the I minus 1th index with a swap at the I minus 1th index. Because of this condition, if there is a swap here, there must be a swap here also to make both the arrays strictly increasing. If there is a swap here and both the arrays become strictly increasing until here, that is nothing but swaps of I. Now, how do I calculate swaps of I? Swaps of I is nothing but swaps of I minus 1 plus this one extra swap. So swaps of I is swaps of I minus 1 plus 1. So I think I have laid clear emphasis on both the equations and justified them. If you have any further doubts, please feel free to leave it out in the comments. Now let us go with the second case. Just a moment. Yes. So let us now go with the second case with a fresh outlook. Yes. So I'll not draw it again, but I'll just roughly show it to you. You have the arrays I, A and B. the index I minus 1 and the index I. So in this case, what is happening is A of I is greater than B of I minus 1 and B of I is greater than A of I minus 1. Essentially, this is greater than this and this is greater than this. So you see, in this case, if you just look carefully, to make both the arrays strictly increasing, you have to just swap one of the either columns. That either you swap here or you swap here. There is no other option to make both of them strictly increasing. So let us say if I swap over here. So let us calculate swaps of I and no swaps of I like we did in the previous case. I think that makes it very simple. So let's say we're calculating swaps of I. So since I'm swapping over here, I need not swap here because of this case. So I can simply say swaps of I is no swaps of I minus 1 plus 1. No swaps of I minus 1 represents the cost to make the arrays increasing until the I minus 1 index with no swap at I minus 1 index. This plus 1 is for the swap over here. Now let us calculate no swaps of I. No swaps of I. Now since there is no swap here, there must be a swap here to make it strictly increasing. Now if there is a swap over here to make it strictly increasing, no swaps of I is simply swaps of I minus 1, because the swaps of I minus 1 represents the cost to make the arrays increasing until the I minus 1 index with a swap here, and there is no extra cost for no swaps of I. So we can simply say no swaps of I is swaps of I minus 1. Let me explain this last case in slightly more detail. No swaps of I is the cost to make the array increasing until the ith index such that there is no swap at the ith index. Now if there is no swap at the ith index, there is no cost for swapping at the ith index. Now we have to make the array increasing until the I minus 1th index with a swap at the I minus 1th index. That is nothing but swaps of I minus 1. That's why no swaps of I is the same as swaps of I minus 1. So we have two more equations over here. Now each time what we will do is we will while calculating swaps of I, we will take this value as well as minimum of this value as well as swaps of I, minimum of this value as well as swaps of S of I minus 1. So that in the end we get the minimum number of swaps and return the minimum number of swaps. Let me reiterate the last point. While calculating swaps of I, we find the minimum of swaps of I and this value. While calculating no swaps of I, we find the minimum of no swaps of I and swaps of I minus 1. So that we return the minimum value finally. I think I made it sufficiently clear. If there are any more doubts, feel free to ask in the comments. Let me just take a moment to see if I can clear any other doubts that come to my mind that would come to your mind also. Okay, I do not see any such doubts, so I think it's sufficiently clear. So just let me just summarize as I did in the last video. Clear frame. So in case 1 was when A of I is greater than A of I minus 1 and B of I is greater than B of I minus 1, right? So let's make a clear distinction. And case 2 is when A of I is greater than B of I minus 1 and B of I is greater than A of I minus 1. See, in this case, one of the options is to do no swaps. In that case, no swaps of I, as discussed earlier, is same as no swaps of I minus 1. Okay, no swaps of I minus 1. And if at all we swap at the I minus 1 position, we have to swap at the ith position also. So swaps of I is nothing but swaps of I minus 1 plus 1. This one plus 1. Let me just explain this equation as it's a little tricky. Swaps of I minus 1 represents the cost to make both the arrays strictly increasing until the I minus 1th index with a swap at the I minus 1th index. One extra swap at the ith index makes it strictly increasing again and in order so that the arrays are proper. So therefore swaps of I is swaps of I minus 1 plus 1. This is sufficiently clear. Let's discuss the cases over here. You can do swaps at either of the positions, either I minus 1 or I, not both. So let us say I'm first calculating swaps of I, which means I'm swapping at the ith position. So which also means I have to make the array strictly increasing until the I minus 1 position, and such that there is no swap at the I minus 1 position because of this condition. So it will simply be no swaps of I minus 1 plus 1 for this one extra swap at the ith position itself. Now let's say no swaps of I minus 1, which means no swaps of I, which means I'm not swapping at the ith position, which means I have to swap at the I minus 1 position and make it strictly increasing until the I minus 1 position also. So it will simply be swaps of I minus 1. Let me give a detailed explanation for this, as I think I fumbled a little. So see, until the I minus 1 position, see, we are not going to do any swap in the last position. So that means we have to do a swap here because of this condition. One swap has to be done, as I told earlier. So we'll do a swap here. And I'm doing a swap here. It has to be increasing, strictly increasing until here. Once I do a swap here, it is ensured it will be strictly increasing until here. So there is no extra cost as no swap is being done here. And there is a swap being done here, and it is being made strictly increasing until here. That is nothing but swaps of I minus 1. Let me go over it again, as I think again I made it confusing. See, my end goal is to make it increasing until here with no swap here. That is no swaps of I. Now, if at all I swap here, until here it automatically becomes increasing. And if I swap here, it becomes increasing until here also. Right? So that is nothing but swaps of I minus 1. There is no extra cost to swap here. So no swaps of I is same as swaps of I minus 1. I would take the effort to explain this again to you. So no swaps of I is basically such that you have to make the array increasing until here. If this is the ith index and this is the I minus 1 index, until here, you have to make the array increasing until here such that there is no swap here. If you're not swapping here, you've got to swap here according to this condition. Only then will it become increasing until here. If you swap here, it will also be increasing until here. And if you swap over here and it is becoming increasing until here, that's nothing but swaps of I minus 1. There's no extra cost here as we are not swapping here. Therefore, no swaps of I is same as swaps of I minus 1. I think I made it sufficiently clear now and summarize the problem to you. Now let me show the code to you. Also, I would appreciate any suggestions on how I should explain better so that my understanding also becomes better. So let me show you the code now. This is the code for the same. Let me submit it. Yes, 148 milliseconds. And one more thing that I missed out is swaps of 0 is 1 and no swaps of 0 is 0, because at the 0th position you can do one swap and still make it strictly increasing. And even if you don't do a swap at the 0th position, both the arrays are still strictly increasing. So no swaps of 0 is 0. I think I've sufficiently explained the problem now, and thank you for watching. Yeah.